I want to talk about testing. That's kind of some of me on the socials if you want to get in touch at a different time. But this is a brief rundown, so there's going to be slightly racing through this because it's a short set. This is a 1 hour talk in a 45-minute slot for a 40-minute talk. So questions, please come and find me if I don't cover anything clearly enough for you. But broadly speaking, I want to talk about property-based testing in .NET. Quick straw poll, who's heard of property-based testing? A few. So I'm relatively new to it, so this is partly about me trying to figure out how to get it working in for .NET programs, but I want to contrast it with example-based testing, so hopefully everybody's already doing unit testing in the kind of classic sense, probably NUnit or XUnit or something similar in .NET land. I want to generalize on that idea a bit and look at how you can kind of augment your testing to give yourself more confidence, and talk a little bit about triangulation. And so triangulation really is just kind of a posh word for doing the same things in two or more different ways to try and expose bugs that way. Property-based testing is quite a good tool for that, particularly at throwing different kinds of data at your method or class or whatever it is. So we're going to get to property-based testing in a bit, and that's a little bit part of what property-based testing is. And I was at another talk recently where property-based testing was a kind of a side issue for that, was that really property-based testing is a bad name for it. All we're really doing, or the most important aspect of it, is randomizing the inputs and generating a random set of data. And I quite like that idea, because we're going to talk about what property means in the terms of property-based testing, but it does have a mathematical term which I'm not going to try and explain. I'm not a real mathematician, or one at all, but really we're talking about generating data. More data than you can kind of think of yourself, hopefully. And then a bit of the other, which is, this is about, I'm going to talk a little bit at the end, if we've got time, hopefully, about writing your tests in a different language to the main language that your code is written in, and why that might be a good idea. So, before we move on to the main thing, property-based testing is quite often regarded as most appropriate for numerical algorithms, because we're talking about generating random data, and random numbers are a thing, hopefully. Yeah, I get an askance look from my wife. So, pseudo-random numbers then. But it's good for more than that, and it's also, all right, another quick straw poll, who's heard of the FizzBuzz problem? More hands, yes. So property-based testing is quite good for testing FizzBuzz, but we're going to try and do something a little bit more sophisticated. Another straw poll. Anybody not heard of Wordle? Hooray! Okay, so Wordle is all about guess a 5-letter word. So here we've guessed a 5-letter word. I chose stare, which luckily wasn't today's word. And the idea is that you guess a 5-letter word and the program tells you which letters you got correct. So the game replies with green letters for correct letter in the right position, yellow for letter exists in the word but you've got it in the wrong place, and then unhighlighted for letters that aren't in the word. So the word that I had, the program, which in this case was just me writing the talk, choose, also wasn't today's word. It was short. So here we've got S in the right position in the first position, so it's a green. T is in the chosen word, so it's in a different position, so it's yellow, and so on. And that's why we get the result we do. It turns out the writing program for this is relatively simple, unsurprisingly, I hope, to most people here. But let's break it down a little bit of what's going on. This isn't the way that Wordle is done. I haven't even looked at how Wordle is done. I tried to do this from, just figure it out in my own head. It might be the right implementation, don't know. This is just what one implementation that I chose of the way to encode how I would determine which letters are green, which ones are yellow, and so The right letter in the right position means that the index that it's found in the set word, the program's chosen word, matches the position in the word that you gave. So the first S is in position 0 in the set word, it's in position 0 in our word, therefore it's green. The T is position 1 in our word and position 4 in the set word. So the found index differs from the index in the word that you chose. And therefore it's yellow. So when the indices match in both words, it's green. When they differ, it's yellow. If it's not found, then you choose something else. -1 is what I chose because that's not a valid index into the array. And I can look at that output array of 0, 4, -1, 3, -1 for any 5-letter word and say that that is a result. And because 0 is in position 0, I highlight it green. Because 4 is in position 1, I highlight it yellow. Does that kind of make sense? So we can write a simple function to do that. So here we've got the guess word. So word is what the computer chose, what the program chose. Guess is what the user has chosen. And for each position, so the in link, the select, there's an overload of that provides a tuple of whatever the element is and its index in the input sequence. We prefer an exact match. So where the found character, its index is the same as the index in the set word, or where we find the index of it and we return that index, and it will return index of, will return -1 if it doesn't find it. So here we'll get 0, 0 for the first S here. And we won't do this is ternary operator. Sorry, I had to mangle the formatting just because to get it on a slide. This is actually a ternary operator going on. So the other arm of the ternary operator won't be executed if the indexes match. If they don't match, we'll do the index of, which will return either the index where it's found or -1 if it's not. And then we just return it as an array of ints. All good? Good, good. So we can write a test for that. So I'm using NUnit. Your mileage may vary. And this is a pretty classic. Given 2 words, when I call my match function, I expect this result, and I assert on it. So hopefully that's reasonably familiar to everybody as a general test. So this is a classic example-based test, where we provide the examples and we assert that the result is what we expect it to be. So here's a more general idea that we might want to test for. Matching a string with itself should always produce the same output, i.e. it's just a sequence of indices where index 0 is in position 0, index 1 is in position 1, and so on for the rest of the string. Okay? And that just says that all the letters are green. We chose the right word. And you get the little bouncy letters in Wordle to tell you that you've won. And we can write reflexivity in kind of layman's mathematical terms. We can write a test for that too. No, it's not a 5-letter word. It should be possible for this test to pass for any length string. It doesn't matter what the string is, we test it with itself and expect that we're just creating an enumerable range of 0 up to the length of the word, and that is our expected result. And sure enough, that passes. I can't see my own notes. So yes, should work for any string, any arbitrary string. And arbitrary is a word that we're going to come back to a couple of times. So here's another more general test. Disjoint strings, so 2 strings that have no matching letters. So I've chosen short and gunge, just because they were the first, short I already had, and gunge was the next word in my little stack of 5-letter word generators. Because I do Wordle a lot, I've got a special dedicated little process going on. I haven't, it doesn't work. But disjoint strings, doesn't matter what strings you choose, they should also have a perfectly predictable result. In this case, it would be all -1s, because none of the letters in one string are contained in the other. So here we're just repeating -1 for the length of the string. And again, this should work for any arbitrary string. Note that we've swapped the words around. We could do that in the test itself, so we could match set with guess, and then we could match guess with set, and we could encode that into test. I've just done it this way because what I really want to demonstrate is that this is a parameterized test. So rather than providing the examples in variables in the test, we're making NUnit provide them and pass them in as arguments to the test. So it's a slightly different kind of test, but it's still an example-based test. So we could write lots of these test case. XUnit uses something called theory, I think, for a similar idea. I'm not sure what MS test does because I've never used it, but we can, we could dream up lots of examples of 5-letter disjoint strings in this case, and we could do the same for, obviously we can do for strings that match themselves and other examples that we could dream up. But I suppose the point is that how many do we have to dream up in order to be confident that that's going to work? So here's a slightly more specific test. One of the properties of the 5-letter word things is that each matched letter is matched only once. So here I've gone back to short and stare because it demonstrates the example better. Again, with the property parameterized test. When we match an S, we only match it once. Each index appears only once in the output array. And so what we're saying is, ignoring -1s, because they could be up to the length of the string of -1, but for matched indices, they should be unique. Yes, no duplicate positions in the result, to put that slightly more succinctly. So far so good, because that test passes for the examples that we've chosen, short and stare. Each index is matched only once in the output. So we've written some example-based tests that demonstrate reflexivity, disjoint strings, and uniqueness of matched indices. And so the hypothesis is, oh, I was expecting a little grin there from, I'll get 1 or 2. Hypothesis is a property-based testing framework for Python. And it's where I first did property-based testing. And the reason it's called hypothesis is exactly this. We come up with the hypothesis that these properties on the left should apply to any pair of strings, as long as they have the same length, it turns out, because of the implementation that I've chosen. But it should apply to any arbitrary any arbitrary pair of strings with respect to the match method. So we can define these as properties in the sense of property-based testing. So the reason why we might want to do that is because here we've identified a counterexample. It's the top one on the test case. Grasp and stash, where grasp is the word chosen by the program, by Wordle, or what other word games are available. Stash is the guess, in this case. And when we try to, when we run the test to the output indices are unique, it fails with, this is again NUnit, XUnit output will be different probably, but what we've expected is that in the output all the elements are unique, but we found a duplicate at position 3. Have I got that the right way? Yeah, so grasp and stash. This is the set word, stash is our guess. If you played Wordle, you probably expect this is the result, that it's found the A and the S as the right letter in the right position, so we get 2 greens, and this S isn't matched. What our function has found is found the S in the first position in the guess word, it's found it at position 3, so it puts in a 3. And then it finds it again because we do have an S in that position in our guess word. So it's matched the same letter, it's matched this letter in the set word twice in the word that we guessed. So, okay, we need to address that. The reason it does that is because when it looks at the S in position 0 of the string, does the index match the one in the set string? No, it doesn't, so it does an index of. Okay, that's the problem. We probably need a more sophisticated solution. So we found a counterexample, but we found a counterexample by churning or popping a few strings off the little process in your head and providing them as handwritten examples to the code, to the test. So we need more precise requirements. Is that a letter in the set word should be matched only once in the guess word, and an exact match is preferred. Now we've kind of already encoded the idea that an exact match is preferred, but our implementation isn't clever enough to figure out whether it's been matched already, or whether it will be matched later on with a better match later in the string. So the solution I came up with, again, I don't know whether this is the real thing. What we're doing here is it's a two-pass solution, so it's not as efficient, but I mean, yeah, shrug. We find all of the exact matches up front and mark them off, and then we loop through the whole string again, and anything that hasn't already been marked off, we're using effectively index of again. It's a slightly different way of doing it, but we're going to be picking off anything that is a -1 in the input array. We're creating -1s or exact matches up here, and then anything that's still a -1 in this loop hasn't yet been matched, so we can do the inexact match and fill in the index that we find it at. You can inspect this later. The talk's not really about this algorithm. The slides will be provided. Can we write a test for the new version? Okay, we can run it through our existing tests. This does now pass the example-based test that we wrote. But we identified a property that should hold for all strings, with the caveat that they are the same length and not 0 length, but we'll get to that as well. How many examples do we think we need? How confident are we that our 3 examples string pairs, even though we've now made it pass, are there other bugs lurking? I'm sure there are, but I haven't tested for them. Property-based testing is about identifying properties that should hold for all the inputs. And often those inputs will be generated randomly by the property testing framework, or you can arrange to generate them randomly. The point is that you're trying to find counterexamples that don't hold. So you define your property. For example, all matched indices in the output array should be unique. And you throw random data at it to see if it can find examples that you didn't think of. And that exposes corner cases that you may not have thought of as well. We're going to talk a little bit about that as well. But the idea is that the more examples that you choose, the greater your confidence that your tests have covered all your cases, hopefully. So enter fscheck, which is a property-based testing for .NET. It's called fscheck because it's written in F#. It's based on QuickCheck, which was a Haskell library. And they called it fscheck because obviously it's not Haskell, it's F#, so it's a no-brainer, the name. But because it's a .NET library, it works for any .NET language, including C#. So the idea is that a property is just a function that tests your assumption. And it can either be a predicate, which returns true or false, or it can be a unit void returning method that throws an exception. In either case, that's a failure. That's simply because an n-unit test, the assert, line throws an exception if it fails the assertion. So it's still a valid FS check property. You can kind of write your own, I can't remember what the syntax is, I never really looked into it very deeply, frankly. It's a bit boring and arcane. But you can kind of hand wire your own property test in FS checks land, but there is an n-unit integration point for FS check, which allows you just to write effectively an ordinary test with inputs, we're going to come to that, that throws an assertion exception at the end, and FS check fails that as a property and says that that is a counterexample. So testing is all about confidence. So here is a simple property in FS check terms. We've got an attribute, instead of the test attribute, or factor, whatever it is in XUnit, this is a property. Now, NUnit also has an attribute called property, and so I've had to disambiguate it. So this is an fscheck.NUnit.property. Shrug, you get over it. And a test that takes a single parameter, and it's a string. And we can test, so this is the simplest one, any string matches itself exactly, and we assert that. And for all, FS check generates, by default, 100 random strings, and the way it generates them is that they can be any length, and it just uses random numbers to pick characters off of the UTF-16 set of characters, so they can contain anything. Runs it through, and if it finds one that fails, it tells you about it. So that's a simple property. Oh, okay, so we run it on our match and it fails immediately. There's a case we forgot. One of the things that it passes in is null, and we haven't tested for that. We haven't even protected our coding against it. So, okay, this is a simple output. What it's telling us here is that after 32 tests of the 100 by default, you can change that to 10 or a million or whatever. If you've got the time to run a million, then fill your boots. And no shrinks. So the other thing that FSCheck does is it tries to find the small, but if it finds a counterexample, it'll take the inputs that it provided and try to shrink them to the smallest representation that still fails that property. I'm not going to talk very much about shrink because it's quite a deep topic. Although quite a lot of research has gone into it. FSCheck is reasonably good at doing it. There are a couple of others that are supposedly better. But what's happened here is it's either it's chosen null as a failing, which in this case it probably was just, we're going to nullate it, see what happens, rather than trying to shrink to it. But after 32 tests, it's already provided 31 strings that pass the property, and it's found a counterexample, and it tells us what it is and then what the error is. So it turns out that's quite important. We're also going to come back to that. Have I got any more notes for this? No. So we can filter our inputs. Obviously we could change our match method to test for null. But actually, at the level that that method exists in a program, it's probably reasonable to expect that the inputs aren't null. And modern C#, we've got nullable reference types, which are a better way of encoding that at the kind of the syntax level. So our match function took a non-nullable string reference. Don't know whether you remember, I'm not going to show it again. But we can also ask FSCheck, when it's generating its random data, to not include null, and empty strings would be pointless. For this, so we want a non-empty string, and that non-empty string type is built into FSCheck as a filtering arbitrary generator, and it will the randomly selected strings it provides will not include null or the empty string. So now this passes. That's fine. All good. So we can say that the property that we are expecting here passes for the randomly generated inputs that we provided. Now, because it's 100, that's probably still more than we would write in an example-based test. So it gives us that greater confidence that our tests are covering the cases that we expect them to. So the uniqueness of matched indexes in the output. This turns out to be a little bit harder to test because we need to curate the input data a little more. I said earlier, this one requires, both words to be the equal length. Actually, more specifically, it requires that the set word is not shorter than the guess, but that's an implementation detail. So we have to provide two strings that have this property, that they are of the same length, is the easiest way to think about it. And disjoint strings similarly have to be the same length, but it requires that those two strings have no matching characters. So again, we need a way of curating the inputs to our property tests. And FSCheck provides us the facilities for doing that. The uniqueness of matched indices, or the requirement that the guess be at least as long as the set word, that's a limitation of our implementation. The disjoint strings, that's a limitation of the test, or the property itself. So those are just a couple of the reasons why you might want to curate your input data, but they demonstrate quite capably, I think, why good reasons why you would do this. So some FSCheck terminology then. An n-unit property throws an exception rather than being a predicate, and the parameter that's given to it, even though so the test that we used earlier that took a string, it's not really a string type. The string type has been hijacked at the reflection level by FSCheck, and it's actually providing an arbitrary string. But we can write our own arbitraries, and an arbitrary, the most important part about it is a gen, which is a generator of t. And they're usually random, but there are generators that can provide you a constant stream of -1s, for example. A generator could be anything that's just providing enough data to fulfill the property. In terms of FSCheck itself, just calls the generator the number of times that it needs to, by default 100. And then the generator is used by arbitrary of t along with a shrinker. So as I said, we're not going to look at shrinkers. And when you're writing your own generators, for complex types, shrinkers can be hard to define. And the default, if you create your own arbitrary type, we'll look at in a minute, the default shrinker is to do nothing. So it will just take the input data as it is. So generating strings of fixed length is kind of the base case, where we want to be able to create basically curated data. And this is this has got a problem, is that this class, the containing class, probably needs to be static. Sorry. But we've got a string of length, which is our generator, that returns a gen of string. And we're using the built-in, arb.default contains all of the built-in generators for FSCheck. And we're taking the one that generates chars. And then for readability in the output, so remember that in the counter example, when it found a counter example, it tells you what data it had chosen for the property. So to make that a little bit more readable, we're filtering that out to be letters or digits. Thank you, Gail. Turning it into an array of Unicode characters, and then creating a string from it using concat. So that's the generator. It's a very, very simple generator. But the important bit here is that it's an array of n size. And so the strings that it generates would always have that length. And then the arbitrary, which is the thing that FSCheck uses to actually plug that data into the property-based test, is calling that generator and turning it into an arbitrary, and that's where there is some reflection magic that goes on. It doesn't actually, it's not necessary to use reflection for that, it turns out. And some different property-based testing frameworks don't require reflection, but this one does. And here we're creating strings of length 15 because they're, I don't know, ever so slightly more interesting than 5-letter words. Possibly opens out the input space so that randomly generated strings are going to be different. Turns out it does, it's not really important. And this is, this is a very simple arbitrary string generator. And when we plug it into a test, here again we've got the property attribute, and we're registering the arbitrary of strings. So that's our class from here, arbitrary strings. And that overwrites what fscheck thinks of as a string generator with the one that we've written. So when we pass in 2 string parameters, they will both have length 15, but of randomly chosen letters and digits. So here we can test that the indices are unique for those 2 strings. For any 2 length 15 strings, we're asserting our hypothesis that matched indices are unique. This test passes. Winners, okay? This is probably about the simplest kind of property-based test that you can think of. And our new implementation passes it. Our original implementation fails this test. So putting back the first naive implementation of the match function, it does fail it after it took it 4 tests to find a counterexample. I mean, come on. It was pretty good, right, if it had to go 4. These are the 2 strings that it put in, and then you get the assertion error in exactly the same way that NUnit reported it for the examples that we dreamed up that we thought would fail that. But the important thing, it tells you the inputs that it used, the counterexample. And using letters and digits, it turns out these are actually more readable than, because the default Unicode set contains all sorts of control characters and so on, which appear as a backslash and then a hexadecimal number. That makes it really, really hard to identify which characters failed the test. This is ever so slightly easier to read, I think. I can't remember which. Position 12, it found, okay, it might be the lowercase y. Anyway, we can now write an ordinary example-based test with those 2 strings, rather than have to keep running the property-based. So it's not terribly expensive to run the property-based test, but we can encode the counterexample strings into, I don't know, you might want to give the test a name to expose the fact that you've really looked at it and keep it as part of a regression testing framework, and say that, you know, this example was identified by a property-based test, who knows. But it's useful to be able to encode that and to literally copy and paste that, the error result, into an example-based test. So property-based testing isn't a replacement for example-based testing. I'm not trying to suggest that in any way. It's an augmentation of it, but example-based testing is still useful for lots of things. So I don't want anybody to take away from this, you should be using fscheck and not NUnit, because that is not the case. So what about generating disjoint strings? So strings that have no matching pairs. Well, this is a brute force implementation where we're using our string of length 15, the generator that we wrote. And then the .2 is an extension method provided by fscheck that means generate a tuple of 2 elements. Unfortunately, current implementation of fscheck doesn't know about the more modern value tuples in C#. So these are the old system.tuple types. But hey, for testing it's fine. And then we're basically saying, using set intersection and excluding any strings where the intersection contains any elements. So we're literally only keeping the ones where they have no matching characters. Oh my God. Okay, and filtering like this can be expensive. It turns out it's not that. It was actually filtering only 1 in 1,000 from my strings of length 15, but I really am going to have to charge onward. About 0 matches. So this passes. I'm also switching to fluent assertions, which is nothing to do with property-based testing. It's just a different way of writing assertions in NUnit. Recommend you have a look at it. It's quite nice. Means exactly the same as the thing below. The fluent-based assertions actually are kind of a close match to F-sharp's native unit testing framework, FS unit, which uses kind of similar terminology. So the observation is that our original counter example, we discovered that manually by kind of dreaming up a string. But the property-based test would have found it for us, so by randomly selecting the inputs. Are there any other properties that we can think of? Well, there probably are, but we're not going to have time to look at it. Testing in a foreign language is quite valuable. So this is the same test for any string matches itself exactly, but written in F-sharp instead of C-sharp. Now the differences here are kind of slightly arcane, but because F-sharp has this idea of piping the output from one function into another, because it is, after all, a functional language, you end up with quite a neat syntax to do that. And then here's one where we register our arbitrary strings arb, and again, we're filtering out things, and the piping outputs into inputs just gives it a slightly different dimension. Custom generator is definitely neater in F-sharp by a long way. In C-sharp it's very, very wordy, but the F-sharp version, so the length of the code is different, and we don't get the syntax highlighting for F-sharp because this is a Reveal.js presentation, but there isn't time. Tests need to be necessary. We've identified some necessary properties. Are they sufficient? So now, I'll leave that to you. Write to me on a postcard if you think they are, or you can prove it, because I can't. But we definitely identified a counterexample in our original algorithm, and I don't know how to determine whether a set of tests is sufficient. There are problems that you can probably prove it for. We think that Kevin Henny did prove it for FizzBuzz, but I still can't quite prove it in my own head. Here are some links. So the slides, I'll make the slides available somewhere. FS-check is here. Please note the documentation for FS-check is pretty awful. It's not really, really awful, but it's not very complete. And that's one of the reasons I wanted to write this talk. CS-check and Hedgehog are other property-based testing frameworks, slightly more modern than FS-check, whose documentation is even thinner, if anything. There is the F-sharp for Fun and Profit has quite a long series of articles about property-based testing in .NET. Most of the examples are in F-sharp because it is a site, after all, about F-sharp programming. But it is enlightening, and it does go into a little bit more detail on ARBs and gens than the actual FS-check documentation does. FS unit, which is the F-sharp equivalent of NUnit, kind of. It's useful to be able to write tests in a different language just because it gives you a different, because of the functional aspect of F-sharp, it gives you a different perspective on what the test should be, and sometimes it will give you a different perspective on what your implementation should be, and because they're both .NET, you can mix and match. And then fluent assertions are available from one at the bottom. If Garth was right this morning that developers don't buy books anymore, then I wrote one at exactly the wrong time. It's not about property-based testing, but it is about C#. Maybe you'll find it interesting. Available from various outlets, your favourite one included. But that's me. Thank you very much.